Welcome to Chapter 4, Section 1. In this lecture video, we'll be getting our first look at systems of linear equations. A system of linear equations consists of two or more linear equations. Here are two examples. Each example has a set of two linear equations, and they are paired together as a system. A solution of a system of linear equations is an ordered pair that we write as x, y, that is a solution of each equation in the system. Let's take this first system of linear equations as an example. Here's what we want to find out. Is the ordered pair 6, 2 a solution of the system? This is also example 1 in your lecture notes. To find out if 6, 2 is a solution of the system, we need to check that 6, 2 is a solution to each equation in this system. Starting with our first equation, we substitute 6 for x and 2 for y. When we do this, we have 6 minus 4 equals 2, which is a true statement. So 6, 2 is a solution to the first equation in the system. Now let's look at the second equation. We'll substitute 6 for x and 2 for y. Doing this, we have 18 minus 10 equals 28. And this is not a true statement. So the ordered pair 6, 2 is not a solution to the second equation. Since 6, 2 is not a solution to both equations in this system, the answer is no. It is not a solution to the system. Let's take a look at example 3. In example 3, we need to find out if the ordered pair 3, 4 is a solution of this system of equations. Let's plug in the values for x and y into both equations and find out if it's a solution. Starting with our first equation, instead of y, we'll write a 4. And instead of x, we want a 3. Simplifying, we have 4 equals 2/3 times 3, which is 2, plus 2. This is a true statement, so the ordered pair 3, 4 is a solution to the first equation. Now let's look at the second one. We'll substitute 4 for y and 3 for x. Simplifying, this becomes 8 equals 9 minus 1. This is also a true statement, so the ordered pair 3, 4 is a solution to the second equation. Since the ordered pair is a solution to both equations in this system, it is a solution to the system. Let's take a look at the graphs of these two lines. Starting with our first equation, we have a slope of 2/3 and a y-intercept at 0, 2. Plotting the point 0, 2, we can then use the slope of 2 over 3 to plot some more points, a rise of 2 and a run of 3. And then connect our line. Now let's graph our second equation. Dividing both sides by 2, we have y equals 3/2 x minus 1/2. That tells us that this line has a slope of 3 over 2 and a y-intercept at 0, negative 1/2. We'll first plot the y-intercept at 0, negative 1/2, and then use our slope of 3 over 2 to plot some more points. Finally, we'll connect our line. Now we find something interesting. These two lines agree precisely at the point 3, 4. Consider that all points on the blue line are solutions to the first equation, and all points on the purple line are solutions to the second equation. Exactly where they intersect is the point where they agree, where there's a solution to both equations. In other words, when an ordered pair is a solution to a system of linear equations, it's precisely where the lines intersect. Now let's take a look at example 4. In example 4, we are going to find the solution of this system of equations just by looking at the graph. We don't know what the equations of these lines are, but we actually don't need to. We can find the solution to this system just by seeing where the two lines intersect. These two lines intersect precisely at the point 5, negative 3. That means that the ordered pair 5, negative 3 is a solution to both linear equations. It's a solution to this system of equations. Looking at example 5, we are going to solve each system of equations by graphing. That is, we're going to graph both linear equations and find where they intersect. Looking at our first line, we have a slope of negative 1/2 and a y-intercept of 0, negative 1. Plotting the y-intercept, 0, -1, we can then use the slope to plot more points. We have a rise of -1 and a run of +2. This is equivalent to a rise of +1 and a run of -2. Now we have plenty of points to be able to sketch our line. Now looking at the second equation, we have a slope of -2 and a y-intercept of 0, 5. We'll first plot the y-intercept at 0, 5 and use our slope of -2 to plot more points. This is a rise of -2 and a run of 1, or a rise of +2 and a run of -1. And now we can draw our line. Notice that these 2 points intersect precisely at the point 4, -3. That tells us that the ordered pair 4, -3 is a solution to both equations in this system. That is, 4, -3 is the solution to this system of equations. Moving on to part C, we have the same instructions. To graph our first line, notice that it's given to us in standard form. We could solve this for y and have it in slope-intercept form, or we can substitute 0 for x and then 0 for y to find our intercepts. Substituting 0 for x, we have 0 plus 4y equals 24, or y equals 6. That tells us that we have a y-intercept of 0, 6. Now substituting 0 for y, we have 3x plus 0 equals 24. That means that x must be 8, and we have an x-intercept at 8, 0. Having those 2 points is enough to draw our line. Taking a look at our second equation, it's given to us in slope-intercept form. So we can see that we have a slope of -3 and a y-intercept of 0, -3. So we'll plot the point at our y-intercept, 0, -3, and use our slope of -3 to plot some more points. Now we can clearly see that these 2 lines intersect precisely at the point -4, +9. This tells us that the ordered pair -4, +9 is a solution to this system of linear equations. Now let's take a look at some special cases. Looking at this first pair of lines, this is what we have seen so far. We have 2 linear equations that when graphed, they intersect at exactly 1 point. This is called an independent system. Independent systems have exactly one solution, and it's precisely where the 2 lines intersect. Looking at this second graph with these 2 lines, they will never intersect. They are parallel. That means that there is no point where these 2 lines will ever agree. This is called an inconsistent system. Inconsistent systems have no solutions because these 2 linear equations will never agree. Looking at this third graph, we only see 1 line, and that's because when we graph these 2 equations, they land right on top of each other. These 2 equations are actually 2 different ways to express the same line. They have exactly the same solutions. This is what we call a dependent system. Every point that's on one line is on the other line. Every ordered pair that's a solution to one equation is also a solution to the other equation. So dependent systems have infinitely many solutions because there's infinitely many points where these 2 equations agree. Let's take a look at some examples. In example 6, we're once again going to solve by graphing. Let's start with our first equation. We could solve this for y and get it into slope-intercept form, or substitute 0 for x and then for y to get our intercepts. Let's go ahead and solve for y this time. Adding 4x to both sides, we have 2y equals 4x plus 10. Dividing everything by 2, we have y equals 2x plus 5. This tells us that we have a y-intercept at 0, 5 and a slope of 2. Now let's graph the second line. Our second line has a y-intercept of 0, -4, and it also has a slope of 2. These 2 lines are exactly parallel. They have the same slope of +2. They will never intersect, so there are no solutions to this system of equations. This is an inconsistent system with no solutions. Moving on to part C, we'll follow the same steps. We can tell by looking at our first equation that we have a slope of -3/4 and a y-intercept at 0, 6. That's enough information to graph our line. Looking at our second equation, let's find our intercept since it's given to us in standard form. Substituting 0 for x, we have 4y equals 24, or y equals 6. So we have a y-intercept at the point 0, 6. Substituting 0 for y, we have 3x equals 24, or x equals 8. So we have an x-intercept at the point 8, 0. When we plot these 2 points, we find that these are exactly the same 2 intercepts from the other line. That is, these 2 equations are 2 different expressions of the same line. So every solution to one equation is also a solution to the other equation. This is a dependent system. So it has infinitely many solutions. This is not the same thing as saying that the solution set is all real numbers, because that's not true. The only solutions to this system are the points on this line. So there's infinitely many of them, but it doesn't include all possible points, just the ones on this line. All points that are on this line satisfy the equation y equals -3/4 x plus 6. So for each x value, its corresponding y value is -3/4 times x plus 6. We can express the ordered pairs that are solutions to this system as x, comma, -3/4 x plus 6. We've written y in terms of x. This is why we use the term dependent system, because the y value is dependent upon the x value. And all solutions to this system are ordered pairs that satisfy this relationship. And that concludes our Chapter 4, Section 1 lecture video.